All right. So yeah, thank you to the organizers for the invitation to speak at this virtual event. Apologies if, yeah, it's very, very early in the morning for me here. So I'll do my best. Yeah, so today I'm going to talk about a paper that I wrote in, I guess, posted the end of May of this year, so pretty recently, with the same title as the talk. You can find it on archive. Let me begin by briefly acknowledging my co-authors. So sort of the theory work on this project was done with Paolo Glorioso, who's a postdoc at Stanford. And then numerical work was done by another postdoc, Joaquin Rodriguez Nieva, and my PhD student, Jinkang Guo at Boulder. Funding from Moore and Sloan Foundations is also acknowledged. Oops. Okay, so since this is a conference on hydrodynamics, I won't say too much about sort of introducing how we should think about hydrodynamics and so on, but let me just sort of say a few words on this. So I would say that hydrodynamics is really an effective field theory, and what it's describing is thermalization. In this talk, I won't sort of touch very much on the field word in that phrase, but at the very least, I think we can agree that hydrodynamics should be an effective theory. It describes many body chaotic systems, and what we're interested in particular is the relaxation of this many body system to equilibrium, or to as close to equilibrium as we can get, given the particular realization of the system with particular conserved charges and so on. Okay. So, the picture I think we should always have in mind is that we've got this box, right, with many, many degrees of freedom in it. And, in practice, we definitely won't know all of the initial conditions. Think about the air in your room, right? You don't know the positions of every single molecule and their velocities and so on. But this isn't important if you want to, make a physical measurement of something macroscopic, like a pressure or a density. That doesn't really matter. It doesn't really depend on positions of every single particle. Instead, what you would say is, my measuring device is really big compared to, let's say, this length scale little l, which is like a mean free path between for collisions between these molecules in air. And so, what? I should just essentially look at physics that's only important on scales that are very long compared to this little l. So let me integrate out all of the sort of short distance chaotic physics in the system. And on very long length scales, I think I'll be left with a much simpler effective theory, which is essentially, or where the degrees of freedom only correspond to locally conserved quantities. Now, why is this? Well, we know, for example, that in our gas, we would have energy and mass and momentum conservation, right? And because the physics is local in space, we can't just take mass and energy from one point in space and teleport it somewhere else. And so keeping this in mind, right, the only thing that we can write down, the only equation that we can write down, let's say for the number density of balls or molecules in this system, right, is a local continuity equation like dt rho plus the divergence of a current equals 0. Okay. And similarly for other conserved quantities. For the usual gases and liquids that we think about, these systems have a sort of approximate Galilean invariance. And so with a bit of simplification, we arrive at, and ignoring energy conservation, we arrive at the sort of Navier-Stokes system, which I wrote down here. Okay. Now, why is this an effective theory? Well, the small parameter in this story is this little length scale L multiplied by the derivative di. Okay, So this is roughly a ratio of length scales, and it's telling us that we're looking on very large scales compared to a sort of thermalization length scale in the system. Okay. All right. Now, this talk is going to be about systems where this notion of what are the symmetries and what are the conserved quantities in your system will be a little bit unusual. Okay. And as we'll see, this will lead to kind of peculiar and interesting changes to hydrodynamics. In particular, let's imagine that we're studying microscopic dynamics, but it's subject to some kind of non-trivial constraint. This will be both a local constraint and a global constraint. And what we're going to focus on today is a theory where we have a global conservation law that not only do I have, let's say, a conserved charge, I'll just call it charge instead of mass for today, but you could say the same story with mass if you wanted, okay? Let's say that I have a conserved charge, and in addition to this conserved charge, I also conserve the dipole moment of this charge, okay? So let's think microscopically about what this would mean. I'm conserving dipole moment, and I also have local dynamics. So supposing, for example, that I've just got some charges moving around on a lattice, okay? So we won't talk about momentum conservation just yet. Just imagine we started with charge conservation on a lattice. This could, for example, be realized by some Markov chain with random walking objects. But now suppose that in addition, I demand that the dipole moment of these charges is conserved as well. So if this is true, right, then an isolated point charge can't move, because if an isolated object moves, then it would change the dipole moment by 1 unit, okay? So I can't move individual objects when I add this dipole conservation law. And I get to this kind of peculiar theory where charges have to move in pairs. So in this example, I have a plus charge and a minus charge. They can move together. That's okay. This conserves dipole moment. If I had 2 plus charges, they can move as long as they move in opposite directions. That would be allowed as well. But there's no sort of individual excitation at the microscopic level anymore, okay? Objects have to move in pairs or more. So we say that because this individual excitation is immobile, we call it a fracton, okay? And there's a very big class of theories that have fracton excitations in them. There are many, many kinds of exotic symmetries and conservation laws that can give rise to this type of restricted mobility. I won't go into that whole zoo. There's a big literature on it, though. I suspect many of you are at least vaguely, maybe have heard of it once in a conference. But there are nice review articles by Xia Chen and Mike Pretko, and then one by Hermele and Nankishore, or 2 of my colleagues. Okay, anyway, so today's talk is going to be about the hydrodynamics of theories with dipole conservation. Now, you might ask at first, how do I know that a theory with dipole conservation can be hydrodynamic in the first place? It's not maybe a priori obvious that that could happen. Maybe this mobility constraint is so strong that the theory just can't thermalize at all. So it turns out that's not true. Okay, you can simulate just a 1D lattice model, with these mobile charges. And as long as you sort of scramble the charges around on 4 adjacent sites at the same time, so you allow for charges to hop, by up to 3 sites in tandem with something else, it turns out that's enough to guarantee thermalization in sort of typical states, okay? So these theories do thermalize, they are ergodic, and we expect for there to be some hydrodynamic description of this. Okay, so about a year and a half ago, with Andrei Gromov and Rahul Nankishore, we came up with a sort of simple prediction for what will happen if you have a lattice model with charge and dipole conservation. And we predicted that there would...
Andrei, sorry. So before going to more details, may I ask one question?
Oh, yeah, sure, that's fine.
Sorry, yeah. So I'm not at all familiar with these fluctuations, and So as a model, yeah, this looks just fine. But are there any realistic material or anything which shows this kind of properties?
So yeah, I will show you a bit later in the talk one experiment that actually realizes what I'm going to talk about on the next page in a tilted optical lattice. So it is definitely realizable. As for what I'll be talking about, this is probably a little harder to realize in the lab, but maybe not impossible. I'll sort of speculate on some ideas. Yeah, I mean, for me personally, I think the primary motivation for studying these things is that, as I'll talk about, they have kind of peculiar hydrodynamics. I think that the sort of deeper one gets into the subject, the more it is a stress test on kind of the conventional Landau approach to hydrodynamics. So I think that, for me at least, the primary motivation for this is sort of abstract. It's to understand the framework of hydrodynamics more broadly. But yeah, this particular dipole conserving theory has actually been realized.
Okay, yeah, thank you.
All right.
Can I ask also a question? So this the microscopic dynamics that you're considering, it's just some stochastic dynamics which conserves dipole. Is that right?
Yes. So you can realize this, for example, by just take, a 1D chain with either empty sites or plus charge or minus charge. And then the update rules are basically pick a pair of 4 adjacent sites randomly in the system, and then replace whatever sort of motif is on that chain with a motif with the same charge and dipole moment. And if you just run this for a long time, you'll find that it's ergodic, the system mixes, and the sort of long-time dynamics is described by this hydrodynamic universality class.
Thanks.
Okay. So yeah, so my co-authors and I predicted this in about 18 months ago, and we claimed that this theory would not be governed by Fick's law for charge diffusion, which is what you might ordinarily expect in a lattice model like this. We said that instead you would see 4th order subdiffusion. Okay, and I think we scooped a few other groups on this result, and about 2 weeks after we posted this paper, 2 other papers came out with numerics showing that there's this beautiful t to the -1/4 scaling in the density correlator. If you just stare for a little bit at this subdiffusion equation, you can convince yourself that that's exactly what you would predict from this hydrodynamic theory. Okay. So
by the way, just a very short, I don't know, maybe strange question, but so you call it just subdiffusion equation, or how you call it, this equation? Because this equation actually very well known among, I myself would call it like you, but among some applied people, and they always call it Mullin's equation. And so it appeared in some surface science, like in 1957 and maybe even a bit earlier. So it's a quite famous equation actually.
Can you send me afterwards? Send me a link, because I'm curious if
I will send you even his paper, I guess, because somebody told me I also met such equation. It was curious, yeah.
Because I'm sort of curious if as I said, I'll sort of maybe hurriedly later in the talk, I'll give an example of an experiment that also saw this 4th order subdiffusion equation, and we were sort of able to post-dict that had to be the result, and it's coming actually from this universality class.
It's those guys, in surface science, they saw it, they have experiments, but with something which are based this equation in 57, and actually, because I never knew myself much about it, I just played with it and I was just shocked. For instance, if you have diffusion equation start with delta function, it becomes always positive, and for this equation there are waves. And there are negative parts and positive parts, even if you just solve delta function. Yeah.
Yes.
It's weird equation. Yeah.
Yeah. Anyway, yeah, I'll be curious to see if that theory also can be kind of understood from this more generic perspective. Anyway, okay. So actually, yeah, also in one of these 2 numerical papers, they did also see that, yeah, the Green's function for this equation is not always positive. Okay. All right, so where is this coming from? It's actually not quite as obvious as you might think at first glance, that adding dipole conservation will lead to this fourth order subdiffusion equation. So one thing you might notice, for example, is that if you take just ordinary Fick's law for charge diffusion, right? We know that has a Gaussian kernel on the line. So you might notice that that kernel actually happily preserves charge and dipole moment. So you might think that you should get lucky that Fick's law will continue to hold even if you demand dipole conservation, because it seems like it's a conserved quantity that you get for free in the continuum. However, there are a few problems with this argument. One of them is that if you put the diffusion equation in a finite box, it no longer conserves dipole moment, and maybe that bothers you a little bit. A more sort of sophisticated argument, well, I'll give you two of them. Okay, firstly, we could ask what are the requirements that we need to have dipole conservation? So we start with just kind of the hydrodynamic version of our conservation law, which is ddt of the integral over all space of xi times the density as a function of x, that's little n now, that should be 0, right? Dipole is conserved. And the only way this is true in general is if the Ward identity for charge conservation no longer just has divergence of J, a current with one index. Now we need a Ward identity that involves the double divergence of a second rank tensor. Okay, so dtn plus di dj jij equals 0. All right, now again, you might ask, well, why not just set jij to be minus a diffusion constant, delta ij times rho, or n here, I guess. So that seems okay, right, from this perspective. But then you notice that jij, okay, once you have dipole conservation, this is kind of your thermodynamic current, right? And so if jij were just proportional to rho, then the coefficient in that term would need to be time reversal odd. And in general, I haven't said anything about time reversal yet, so we should assume we have that as a space-time symmetry, and therefore we can't write down that term because there's no time reversal odd prefactor that we can write down. Okay, so that blocks Fick's law, and the next thing that we can write down is a term with two derivatives, which is what I've written here, and that one turns out to be okay. Now, it turns out that if that argument also is a little bit fast, there's an even more serious way that you can see that jij has to involve a two derivative object. And this is because if you want something like a local fluctuation dissipation theorem to hold, right, the current which needs to have local white noise is jij. So this little Cij thing, that represents the stochastic sort of white noise in my current. For that to be local, I have to have two derivatives sitting in front of the density, just like the noise in an ordinary current, right, tells me that since it's divergence of J, the gradient term will have one derivative. So it's kind of the same story here, but with this higher derivative object. All right, so that's sort of the most sophisticated argument that we have for why you have to get this fourth order subdiffusion. We've also derived this using these kinds of modern Schwinger-Keldysh effective field theories for hydrodynamics. I won't say anything more about that, but you can read our paper. It's kind of a nice little argument, and I think it really helps to convince you that this answer has to be correct. Okay. In addition to studying this dipole conserving theory, there's a whole infinity of different universality classes with exotic sort of multipole conservation laws. So these would be cases where, for example, you conserve quadrupole moments in addition to dipole and charge. And you can also do things like charge conserved on every line in a square lattice. And that gives you subdiffusion, but with some kind of funny anisotropic derivatives. So there's a whole zoo of these things. And at least when you're talking about sort of charge conservation plus something else, the formalism in this paper should be sufficient to sort of determine the universality class that you expect. Okay. And all of these universality classes are stable. So all the corrections you can write down to this theory are irrelevant. Okay. All right. So we sent this paper out for review at a sort of glossy journal, and the reviews we got back, I was a little bit surprised by. And roughly speaking, they said that, this is pretty cool, but it's not hydrodynamics because hydrodynamic things have momentum conservation. And so therefore, this isn't very it is not general interest, right? So, so at the time, I was a little salty about this, but I mean, I think in common parlance, right, it is true that normally we think about the Navier-Stokes equations as fluid dynamics. And so it's sort of a cute question, right? If you have a fluid with momentum conservation, but you add on top of that charge and dipole conservation, how do these Navier-Stokes equations get modified in the presence of this additional conservation law? Okay. There are slightly less sort of playful motivations for studying this question. So in the field of sort of fracton quantum matter, one of the big puzzles, especially to the sort of high energy crowd studying this question, is whether or not these theories can be coupled to gravity. Can you put fracton theories on general manifolds? It's not at all obvious that this is the case, it turns out. And the stress tensor actually couples to gravity in quantum field theory. And so if we study theories with dynamical stress tensors, which include fluids with momentum conservation, we may get some hints as to the relationship between what kinds of gravitational theories you can couple to fractons. So that's kind of a more sophisticated motivation rather than just as kind of bitterness at a referee for studying this problem. But whatever the motivation is, we'll see that it's a nice problem in its own right, and it has some sort of surprising conclusions. So it was very much worth doing in retrospect. Okay. Oops. Okay, so let's think about what we might expect before we get started. So we're interested in the hydrodynamics of a theory where the conserved quantities are the momentum, capital Pi, which is going to be the integral over a momentum density, which is pi I. We have a total charge Q, which is the integral over all space of a charge density n, and then the dipole moment, the integral over density times xi. Now, there's an algebra that relates these things that's called the multiple algebra. I mean, this is kind of the simplest non-trivial case of a multiple algebra. And here I'm using classical Poisson brackets. You can use quantum commutators if you prefer. Obviously, it's equivalent up to an I. The multiple algebra relating these objects tells you that Q commutes with everything, but dipole and momentum do not commute with each other. The commutator of dipole with momentum is proportional to Q, okay? And we should expect that this last non-trivial Poisson bracket is going to make hydrodynamics subtle, okay? It will make hydro particularly delicate, I would say. Even without momentum, we already saw, right, that we had to get this sort of this higher rank current, this Jij, rather than just a Ji. But this last commutator, right, it's a little tricky. We do have classical examples of fluids, right, with conserved charges that don't commute with each other. And the right example to have in mind here will be an isotropic fluid in, 2+ spatial dimensions, okay? So when you have an isotropic fluid, right, you have angular momentum conservation. That would tell you that an integral over xi pi j minus xj pi I, that kind of anti-symmetric combination of x and pi also is the density of a conserved quantity. And we know that in that case, you don't get an additional hydrodynamic degree of freedom, right? You get some kind of additional constraint on the degrees of freedom you have. In the case of the isotropic fluid, we learned the stress tensor should be symmetric up to total derivatives, okay? So this is going to lead to sort of similar effects, but they'll be a little different as well. Okay, so we expect, we actually first sort of studied this question using field theoretic methods, which we have not written up yet, but we probably should. So let me sort of tell you the revisionist version of the story, which is a bit closer to sort of standard Landau kind of reasoning, but sort of being careful about this multiple algebra. So we expect that our hydrodynamic equations, right, we're going to have this funny ward identity for density with a second rank current. Okay, that's demanded by dipole conservation. But a priori, you know, we should expect just a usual stress tensor for momentum. Okay, I'm also not going to consider energy. We think that this actually changes the universality class if you add energy conservation and makes it not so interesting. So let me not talk about that case. Okay. So we just have density and momentum as our conserved quantities. And now we have to ask, what are the constitutive relations for J and T? And here's where this kind of funny commutator between dipole and momentum becomes really important. So if you think about what that commutator implies, and here's where, at least for me, quantum mechanics might be a little easier. You could think about applying a unitary to your system, something like e to the I, ci, little ci contracted into di. Di is a global conserved charge, so this shouldn't really do very much. But what it's going to do is it's going to shift your momentum density by ci times n. Now that's okay, right? Because pi is a conserved density, n is a conserved density, so there's no contradictions here. But it does tell us that, right, the momentum that we associate with our theory is in some sense not that well defined. Okay, and so this is sort of a little subtle. It also implies a shift to the stress tensor, not maybe quite as interesting. Okay, but one thing we learn is that we should probably write the equations in terms of a velocity-like field, little vi, which is going to be pi I divided by density. This will shift by constants, right? And that means we kind of know what to do. We should just demand that all of the hydrodynamics, all of the things like entropy densities, pressures, and so on, none of them can depend on the absolute value of vi. They can only depend on derivatives. Okay. So we conclude that, for example, if we look at entropy density, that should be a function of n and di vj. Okay. Now, at this point, we can turn the crank of hydrodynamics. Okay. We can try to ask that there's a notion of entropy current, which is conserved at ideal fluid level. This is slightly awkward because we didn't have energy conservation, but we can make it work. Okay. And what we find is these kind of ugly looking equations that I'm not going to read to you, but I just want to say, I put them down here just to emphasize we've actually done this properly. Okay. So there's a kind of funny structure to this theory at the nonlinear level that we've sorted out. Okay. Now you can go to first order in a derivative expansion, right? Just, we want to get things like viscosity. What's the analog of that in this fluid? Well, it turns out that there is something kind of like viscosity in this fluid. There is this eta coefficient here in red, but you'll notice that it doesn't couple to little v, it couples to this object capital V, which if you sort of read through the chain of equations is more complicated than just momentum density this time, okay? So there's some subtle changes between this hydrodynamics and the sort of conventional Navier-Stokes equations. Okay, unsurprisingly, we have this kind of fourth or Jij couples with two derivatives to the gradients of mu. That's probably not too surprising. There's some off-diagonal terms that are allowed, and then there's noise as well here in blue. And a standard fluctuation dissipation theorem holds. Okay, so C correlators look like white noise with the coefficient proportional to C, and so on. Okay, so let's look at the linearized hydrodynamics in this theory. Okay, so if you read through those equations and you sort of think about them carefully, what they'll end up implying to you is that, again, dropping all the order 1 constants here, this is purely schematic from here on out, the hydrodynamic equations have a kind of funny structure to them. So if you look at the density equation, this Jij current basically contains a term like grad pi, and then two derivatives acting on density. Okay, so that's my first line in the equation. In the second line, I still have a gradient of pressure, so din is still there. Okay, whereas it turns out that now viscosity gives me a fourth order in derivatives contribution. So I have four derivatives acting on pi, and that's my dissipative term for momentum. Okay. So what are the hydrodynamic modes in this theory? We can just turn the crank at this point. So longitudinal momentum as well as density, just like in an ordinary fluid, these things combine to form a sound-like mode. But in this case, the sound mode has a quadratic dispersion relation, so plus or minus k squared schematically, rather than plus or minus k in an ordinary fluid. And then we can subtract off I times k to the 4. Okay. So the leading dissipative correction is fourth order, which maybe in retrospect doesn't surprise us at all, right? It's the same fourth order we found in the lattice model without momentum. Okay, so same power law here. For the transverse momentum modes, we find that they are also fourth order subdiffusive. Okay, and so now we learn our first scaling dimension for this hydrodynamic effective theory, which is that the dynamical critical exponent z is 4. Okay, so now we can ask, is this hydrodynamics actually stable? So we're working in d space dimensions here, okay, and then one time dimension. Within linear response, if we just do the calculation, it's pretty straightforward from here on out. We find that the density has scaling dimension d over 2. The momentum density has scaling dimension d over 2 minus 1. And the two noises in tau and xi turn out to have the same scaling dimension of d over 2 plus 2. Okay. All right. And we have z equals 4. So just like in an ordinary fluid, we should think about so what might the most scary form of nonlinearity be here? And there's a bit of a, we have some guidance on what might happen. If we think about an ordinary fluid in 1 plus 1 dimension, so d equals 1 space dimension, right? We know that if you add pressure nonlinearities, so term in the pressure that's proportional to density squared, or at least deviations in density squared, right? That turns out to be relevant. And it means that hydrodynamics doesn't exist in the 1 plus 1d fluid. You have a strictly relevant operator that flows you to the kpz fixed point, right? So here we could ask, what about that same pressure nonlinearity? This turns out to be the most relevant term for us as well. And it turns out to have a scaling dimension of d over 2 minus 2. So this prefactor P2 in my Taylor expansion and pressure, that turns out to have a negative scaling dimension below 4 dimensions. And so for this reason, we say that hydrodynamics doesn't exist below 4 dimensions. Okay, we don't have this nice derivative expansion. There's an instability to some what we call the dipole kpz fixed point. Okay, and in some sense, this is kind of the punchline of this talk. Okay, by studying a fluid with these non-trivial symmetries and conservation laws, we can find new universality classes both for hydrodynamics and for non-equilibrium physics. Okay.
So sorry, may I ask one question? Maybe
Sure.
I misunderstand this something, but what do you mean by this universality class? So in the case of KPZ, for example, so the equation contains noise, right? But,
Yes.
and with only hydrodynamic equation, we don't
have
really
noise in our equation as well.
Oh.
So if I go back here, there is noise in.
Okay. Oh, so sorry. Yeah, I missed it. Sorry.
Yeah.
Okay.
So yeah, I mean, we I think it's really analogous to KPZ in many respects. So yeah, we call this the sort of dipole KPZ fixed point. All right.
Hydrodynamic part is like a Burger's equation thing.
Well, a little bit, but with everything, like there's a lot of higher derivative things floating around. So it's a little weirder than the usual Burger's equation, I would say. But the kind of what drives the instability is quite similar in some sense. Yeah. All right. So in the last 15 minutes or so of the talk, let me try to address the question of, now that we've predicted this universality class, does it actually exist? I mean, can you actually look for this? And happily enough, the answer is yes. So for the most part, I'll be talking about numerics here. I have to say maybe 30 seconds about experiment, possible routes to finding this in an experiment, but I hope someone is more creative than us along those lines. But at least if you just asked, can you even find any physical model at all that has dipole and momentum conservation? It's actually not so obvious, I think, at first glance that this would be possible, because if you think about, just moving particles around, how can we said before, an individual particle can't move, right? Dipole conservation says individual particles can't move. So it turns out the way you do this is sort of deceptively easy. So consider the following Hamiltonian system. This is going to be a one-dimensional model. And the only thing I'm going to do, it's going to consist of nearest neighbor particle, or particles on a line. They interact with their neighbors. Here, X means displacement out of equilibrium. Okay. Anyway, the only thing you have to do to give this model dipole conservation is modify the kinetic energy. So rather than being p squared over 2, it's just pi minus pi plus 1 squared over 2. And this gives you dipole conservation. Why? Well, remember that ordinary momentum conservation just came from having a shift symmetry where if you move all the coordinates by the same constant, it doesn't change the physics. This is exactly the same. For dipole conservation, you just have to be able to shift the momentum, all the microscopic p sub i's by a constant. And if you have that shift symmetry, you have dipole conservation. Okay. And this is basically the microscopic analog of this funny pi going to pi plus c times n shift symmetry that we had in our continuum hydrodynamics. Okay. Now, this theory being Hamiltonian has energy conservation, and if we want to be really strict, we don't want that. So we can basically just add noise and dissipation to this model, just stochastic terms, basically write down Hamilton's equations and add some noise that breaks energy conservation, and we'll call that result model A. Okay. Strictly in practice, I should say, we're typically going to turn off the noise. It seems that for timescales that are numerically accessible for us, noise doesn't really do that much. It actually sort of makes it harder to see what we're after. So yeah, I'll come to that in a few minutes. Okay. Before I show you numerics, though, let me point out that this model A is not quite as weird as you might think. So we actually were brainstorming this, and it was purely just some abstract construction. But after a few months of sort of starting the simulations and so on, we realized that actually there's a few analogs of model A of our model A, not the Hohenberg-Halperin one, of course, in the literature. So for our model A, one analog, which is not perfect, but it's good within linear response. One analog is the Heisenberg Ferromagnet. So here's my Hamiltonian, right? I have classical sort of SO3 spins interacting with each other on a lattice with the usual Poisson bracket. If you expand around a background with constant SZ, right, we would expect Magnon fluctuations within linear response. And it turns out that the conservation laws for Sx, Sy, and Sz become analogous to dipole momentum and Q. Okay. Now, at the nonlinear level, these models have a different structure. So yeah, I would say the only thing thus far that we can understand is that sort of very sophisticated way of understanding the k-squared Magnon dispersion relation is that it's a consequence of this sort of accidental momentum and dipole conservation. So that's sort of particularly pretentious way of understanding that well-known result. It would be interesting if one can sort of add perturbations to the Heisenberg Ferromagnet that kind of stabilize SZ to be roughly constant while adding nonlinearities for Sx and Sy. If you did that, then perhaps the ferromagnet can realize our universality class, but we don't know if that's possible. Okay. Another analogy here, which is maybe a little weaker, is that there are sometimes models that are called dipole fermion models in quantum Hall systems, and these also have the momentum shift symmetry that I mentioned earlier. Typically, they're a little more non-local in space, though. But anyway, these are two models that effectively have a kind of momentum shift symmetry in them. The other model that we've considered is a model where you don't have momentum and dipole symmetry microscopically, but we expect that they'll emerge in the long wavelength physics. So model B is a model where we expect momentum and dipole to be approximately conserved. The model here is going to have similar interactions to the earlier one, but we're now going to replace the kinetic terms with essentially this single particle piece minus cosine pi minus f times xi. And we'll take this parameter f to be very large. So what does this mean physically? Well, if we turn off the interactions, what happens, right? We've got a bunch of particles on a line, and they are essentially, it's like they have a kinetic energy like coming from a low-lying band in some lattice model, right? So like cosine momentum kinetic energy. And then we've turned on a very strong external force. And we know that this will lead to Bloch oscillations. Okay, so these particles are going to oscillate back and forth forever in the absence of interactions. And you can sort of think of this as like an emergent dipole conservation. I mean, it's a complete freezing of the dynamics without interactions. But one way you can think about this is that in this Hamiltonian, right, the term which dominates is minus f times xi. And what is that telling me? That's telling me that energy and dipole are sort of almost the same thing. Right. And so in this model, we expect energy conservation is going to roughly morph into dipole conservation. As for why we think overall momentum is conserved, well, that's maybe a bit more of a spirited guess. But it turns out that if you take a solution to this model, which is sort of coherent Bloch oscillations plus little perturbations, you find those little perturbations do have our k-squared dispersion relation. And so we sort of conjectured this model might also lie in the same universality class as model A. And yeah, so we simulated it. Before I show you those numerics, let me just very briefly comment that this kind of model is actually maybe not impossible to realize in the lab. If you take away momentum conservation, this was done 2 years ago. So you can put fermionic atoms in a tilted optical lattice. And when the tilt becomes sufficiently strong, they see a crossover from basically ordinary charge diffusion to this fourth order subdiffusion. And as I mentioned earlier, we post-dicted this. We demonstrated that what happens in this model is that energy conservation morphs into dipole conservation. So this one lies in the same universality class as the Markov chain on the 1D lattice with charge and dipole conservation. Okay. Anyway. Let me show you the numerics for models A and B. So the way we do this is we start our initial conditions with basically random positions and momenta for the particles. And we think that basically if we look at sort of the typical scale in the structure that we see over time, that typical length scale should increase or the wave number should decrease. And why is that? Well, within linearized hydrodynamics, right, if we have density fluctuations on wave number k, they're exponentially decaying with a decay rate that's going to be k to the 4, okay, within linear response, where z equals 4. So we expect that the typical wave number in this theory is going to be roughly t to the minus 1 over z. And so we simulated both of our models, once with a pressure term that had a cubic nonlinearity and once with a pressure term with no cubic nonlinearity. Okay. And these models roughly correspond to setting this most relevant nonlinearity P2 to be 0, that's in red, or not 0, that's in blue. Okay, so not 0 has the cubic term in V. And if we look at the scaling of this typical wave number, we see that it's pretty substantially different whether or not we have this cubic nonlinearity. Okay. When we don't have the cubic term, that's when we think P2 equals 0, we find that the Z in our model is approximately 4, okay, based on this test. So it seems that we're fairly close, if not right on the nose with our previous prediction. We actually think that theory should also be unstable in 1D, but not as unstable. Anyway, we can't really tell the difference from linear hydrodynamics in this numerics. However, when we turn on this cubic nonlinearity, we definitely notice that the universality class has changed. And now we see that the dynamic critical exponent is seeming to be approximately 2.5. Now that 2.5 is exciting to us because there's a very crude scaling argument that actually predicts 2.5 should be the ultimate critical exponent. So the way we argue that is basically we say that the dissipative term, I believe in the momentum equation, that one should become irrelevant, and the term which should govern the fixed point scaling is instead this quadratic nonlinearity and pressure. And if we sort of recalculate what all the exponents need to be so that all the right terms are sort of exactly marginal, we find that Z would have to be 2.5. A similar argument seems to predict 1.5 for the KPZ exponent exactly. We don't think that should be an exact argument for our model, but it's sort of curious that it seems to get close. In model A, where we have a little bit more numerics and they're a bit easier to interpret because there's not emergent conservation laws, we've also looked at the Magnon dispersion relation, the sound dispersion relation. We can see that it has a nice k-squared dispersion with this k to the 2.5 decay rate. And oh, maybe by the way, as a quick comment, I think those of you familiar with KPZ won't be too surprised by this, but we don't say that this dissipationless term, we're not going to count that as a relevant operation or a relevant term in the equations. We should only want dissipative or nonlinear terms to be counted in scaling. Anyway, we do see that this k-squared doesn't, the speed may well be renormalized, but k-squared doesn't seem to actually change. It's just the dissipative exponent that seems to change, okay. Which is good because we were not counting that dispersing term in our scaling argument. Okay, one final curious feature about this model, we don't actually understand whether there's something interesting or subtle here or not, but I'll just mention it. The momentum susceptibility in this model you can show has a quadratic divergence, okay. And when you have something like this, you may think that there's a sort of Merman-Wagner type theorem, okay? Like the simple example of this would be a Goldstone boson. And of course, in a one-dimensional model, you would say that when you have this kind of susceptibility, you have maybe some classical tree-level symmetry breaking, like a Mexican hat type potential. But then you would say that this divergent susceptibility means fluctuations are so strong that the symmetry will be restored, okay? In this case, there's not an obvious symmetry breaking associated. I mean, momentum is just conserved. I don't think there's any symmetry breaking in our system. And yeah, also this is a non-compact space, so I don't really know what it, well, yeah. I don't think the Mexican hat analog is sort of that appropriate. But one thing, I mean, we definitely do see this quadratic divergence and susceptibility. We look at 2-point functions of, fluctuations of momenta in equilibrium. Again, model A has the sort of crisper numerics for this. Yeah. One thing you might ask is, does this mean hydrodynamics doesn't exist? Because what this does mean is that the momentum density itself is not really a well-defined degree of freedom. in equilibrium. Its fluctuations are just too big. In 1D, you would expect the average value of pi is like square root L in system size. However, we think that this doesn't matter that much because thermodynamics only couples to gradients of this V field, which is like gradients of pi, and then those would have a finite susceptibility. So anyway, we don't know whether there's anything interesting with this, but it is a sort of curious feature of this universality class. All right. So with that, let me conclude. So to summarize, we found a new non-equilibrium universality class, which we call the dipole KPZ fixed point. Infinitely many more of these will exist, okay, because there's lots of other multipole conservation laws, etc. When you add momentum conservation, these will also be unstable, oftentimes up to arbitrarily high dimensions for the right type of symmetry. So we expect sort of a whole zoo of new universality classes await. And I've mentioned this already, that maybe understanding this will help us to understand gravity and its relation with fractons. The last thing I'd like to emphasize is that I believe these theories will give us some deeper insights into the nature of hydrodynamics. There are a lot of cartoons with fracton fluids where it seems like you can give arguments that suggest that either one or both of a sort of Landau style arguments have to be wrong. And so I think understanding these fracton fluids will give us a much deeper understanding into the origin and sort of the nature of hydro as an effective theory. All right, thanks. Happy to take questions.
Okay, thank you very much for the very nice talk. Yeah, I think so. Yeah, we get some questions, comments, and there's already one person.
May I ask a question?
Yeah.
Yeah.
Sorry, there's one before you. Sorry, can you wait a minute? Yeah. Shankar, please.
Yeah. This in your equations, I mean, what you are finding is something like a long time tail, isn't it? T to the power minus 1/4. But is it because you do not have Galilean invariance in the system? The usual one is not showing up. Would that be a look at it? Isn't it like a long time tail that people know for usual classical liquids? But of course, that comes from the Galilean nonlinearity, the famous paper by Kosterman and System.
I mean,
but in this case, it is because that Galilean term is not there, or maybe I don't know. My feeling is it because that Galilean invariance term is not there? You are finding this kind of.
I mean, so if we go all the way back to this t to the minus 1/4, I don't think this isn't a long time tail. This is just a regular 2-point function.
Yeah, the regular 2-point function has a long time tail.
Well,
because
okay,
the nonlinearities, and that goes as t to the power minus d by 2 and things like this in usual hydrodynamics, and that comes from the Navier-Stokes nonlinearity, which is the Galilean term. Now that I guess you do not have there, so I believe that is giving rise to this kind of thing. It's the same sort of long time tail effect, but it is producing the t to the power minus 1/4. Would that be wrong?
I mean, I would say that, okay, so in some sense, it is the way the nonlinearity enters into and drives us to our fixed point is very similar to what happens in an ordinary fluid, but with sort of z equals 2 replaced by z equals 4. So to the extent I understand your question, I think the answer would be sure that it's kind of similar. But yeah. I mean,
this density nonlinearity that you are getting here, this gives rise to the usual mode coupling theory of glass, the density nonlinearity, the Pn square, delta n square, in the pressure term, in the usual fluid. That's what gives rise to the mode coupling nonlinearity. I mean,
so this P2 term, I mean, both for the ordinary fluid and for us is sort of the most important nonlinearity.
But the usual t to the power minus half comes from the momentum nonlinearity. And I mean, why is Galilean invariance ignored in this time? I mean, is absent in this model? Then
I mean, why Gaussian invariance doesn't exist here. I mean, I don't think you can reconcile that with this multiple algebra. I haven't thought about it deeply, but yeah, I suspect that,
because these are macroscopic equations. So what is the reason of?
Sorry, you can't have Gaussian invariance here because the current can't be proportional to momentum, because the current itself is always a total derivative. So yeah, the charge current is always a total derivative. So
Okay, maybe we can go to the next question. So David, please.
Yeah, in standard KPZ, it's nicely formulated as a stochastic PDE. And you're saying you have a new dipole KPZ, but you didn't display the new dipole KPZ equation.
So they are here. If take this continuity equation with these zoo of equations, and this is the close. I mean, this is the PDE formulation that we have. I know there are other forms for KPZ, like there's other interpretations of that as well.
But that's just linear, isn't it?
No, these are very nonlinear equations. I mean, S could be some nasty nonlinear function, VI pi j, right? There's all kinds of nonlinearities.
But the question is, could you, with KPZ, it's been distilled down to its essence, and there's only the one nonlinearity written in there that's essential to it, and so it has a compactness. And I just wonder if you understand this enough to make a nice version of it, that
we tried and we were unsuccessful.
Linearity like KPZ that contains the essence of it.
Yeah, we tried to simplify these equations a bit. We were not successful in doing this. I'm not going to say it's not possible, but it's probably more complicated. I mean, one of the subtleties is just that I think one of the things that helps you with KPZ is that you have I think having the dispersing mode being linear rather than quadratic in K seems to help with sort of distilling the equations down. It's been many months since we tried, so
I see what you mean. So you're saying,
yeah,
you're saying when you go from 1D nonlinear hydrodynamics to KPZ, you go to the moving frame of the waves, and then you take away the linear dispersion, and you don't have a similar operation that you can do.
We tried, and I think we were able to do it. It looks a little more non-local because of the K-squared dispersion that you have to undo. But even with that equation, we weren't able to solve it exactly.
No, I didn't mean solve it. I just mean display some simple version of it.
Oh,
not
maybe we were successful at that. I would have to go look at our notes. But.
Yeah. Okay.
Okay. So then, Jacopo, please.
Yes. Hi. Yeah. So model A is classical Heisenberg chain, right?
Not quite. At the nonlinear level, they do differ in important ways.
Yeah, right. So indeed, okay, the other one before. That's the okay, right.
Yeah.
Yes, but okay, but then maybe I just missed it. But what is your then? I mean, what are the physical consequences for the transport in this model? Like, so is there still? I mean, can you still claim that there is like a quasi-conserved dipole that, and therefore, like, again, some transient between two different dipole transport?
So, okay, there's a few subtleties with the Heisenberg analogy. One is that, the ferromagnet is sort of, that ordering doesn't exist in 1D in the thermodynamic limit. And so that's a bit awkward for this analogy. I would say, honestly, the only thing at the moment that I would feel comfortable saying is that one way of understanding the K-squared Magnon dispersion relation, not the only one, but one way of understanding it is that it comes from this identification written here, that the sort of around a background of constant SZ, the dipole momentum algebra is equivalent to SO3. It's maybe a little bit contrived, but
that's just Golson modes, right?
sure, yeah. As I said, it's I mean, the important thing is the nonlinearities in each of these systems, and those differ. Now, the reason I bring it up is maybe it's possible to imagine a model where the SO3 symmetry in Heisenberg is broken explicitly at the nonlinear level in such a way as to kind of make SZ approximately constant, and then having SX and SY sort of fluctuating but interacting. Maybe that could realize our new fixed point in one of these magnets, but just the simple Heisenberg model won't do it. I do recall actually that we had a very hard time finding papers on, I mean, it was written back in Hohenberg and Halperin that this kind of model had a rather high upper critical dimension, and it seemed as though people didn't know very much about the endpoint of various instabilities within hydrodynamics, but we didn't really make much sense of that literature, and we haven't connected it with what we're doing, whether that even is possible.
Okay, thanks.
Okay, so next, Abhishek.
Hi. So I had a question on model. If you go to the previous page.
Mm-hmm.
Right, yeah. So, I mean, so in this case, I just wanted to understand the dynamics. So if I just had the usual kinetic energy, then of course one knows exactly how to write, let's say, nonlinear fluctuating hydrodynamics and compute everything. So in your model, the dynamics is Hamiltonian, and then in addition, you have noise, which destroys energy conservation. Is that right?
Yes.
And so the only conserved quantities are then, I guess, yeah. So what are the conserved quantities?
Dipole momentum, and then the number of particles n is sort of trivially conserved. So dipole momentum and charge are all conserved in this model. The algebra of conservation laws is equivalent in model A is to what I showed earlier.
Okay, so momentum, number, and dipole. Okay, so and so you need, I mean, you could have a completely quadratic model, right? I mean, if you have, because anyway it's stochastic, so it's probably going to be ergodic. So in principle, for the potential, you could.
It depends on the nature of noise, I think, but maybe.
Okay, and so for this model, I mean, one should be able to write the hydrodynamic. So you have the exact hydrodynamic equations for this, or it's exactly what you showed earlier.
Okay, if I set G and G prime here to 0, yeah, we can solve it exactly, and you get propagating k squared modes. You know, with some, it's like 1 minus cosine k or something is replacing k squared. Right. As I said, I think the way, if you add noise in sort of the wrong way, probably you just get a bunch of decoupled, whatever the OU stochastic process is, just one for each Fourier mode. So you need to do something a little more complicated to induce interactions between modes, but.
Okay, I guess, I mean, you just need to introduce noise which conserves the other conserved quantities and destroys energy conservation, right? That's all you need.
Yes. Yeah, we talk about it in the appendix of our paper.
Okay. Right, okay, thanks.
Okay. Yeah, I'm also still curious about trying to make more, comparison between your model and KPZ. So first, as Abhishek asked, so in the case of KPZ equation, also there's only one conserved quantity, right? And in your case, there are 3 conserved quantities. Is it correct?
Yes.
So in that case, the situation sounds a bit similar to fluctuating hydrodynamics by Hilbert and so on. Is it, do you know it, and would you kind of agree?
Sorry, what was the end of the question?
Well, so in the case of fluctuating hydrodynamics, there are three conserved quantities. So one has to go to kind of normal modes. And in a most generic case, maybe three equations for each normal mode, maybe like KPZ. But if there are some symmetry and so on, so then some of the equations do not go to KPZ, right? So yeah, so in which sense can you draw analogy between your model and the KPZ equation? That's my question.
So, I mean, I think for us, if we take out the dipole conservation, we get a sort of Burgers-like equation, and then that one should flow to usual KPZ. But the dipole conservation in this model is delicate because it's not leading to a new dipole conservation doesn't give you a new propagating degree of freedom. It's because dipole charge is the integral of xi times another hydro mode. So if you imagined like having some dipole density as an independent degree of freedom, it would just relax into n that you can show on sort of general principles. So in that sense, it's sort of a bit different. This is sort of analogous to like a Burgers equation without energy conservation, which mathematically you can certainly write down. It's fine. Yeah, here the additional symmetry comes in, like demands all these peculiar derivatives in these two equations, like having these 3 and 4 derivative terms instead of 1 and 2 derivative. That's the consequence of dipole conservation.
Then, because when you talk about dynamical exponent, then do you look at kind of one particular degrees of freedom, or?
So for the dynamical exponent, we say that is fixed by the decay rate of our modes. And as long as we don't have energy conservation, it's always k to the 4. With energy conservation, you can get k squared decay terms as well. So we think that's a different universality class, which is not as unstable as this one. Yeah, but we're not counting this k squared as a. We're not saying, we're saying this doesn't contribute to Z in the spirit of, in KPZ that you could go to the wavefront of a propagating magnon and ask about fluctuations there. Again, it's a little more delicate because you can't do that with a simple coordinate change, but we think sort of a similar principle is still appropriate, even if in practice it's more difficult to carry out.
And so, yeah, maybe still kind of analogy. So in the case of KPZ, in the original paper by KPZ, they try to use the dynamic denormalization group argument to predict the dynamic exponent. And in the case of 1D, they found 3/2 or something, right? So for example, can you think of applying similar techniques to predict a dynamic exponent?
So I don't remember if we've done this calc. Like we're basically planning to write a sort of longer field theory paper, and it's possible we'll sort of do that in that paper, but I'm not entirely sure. We certainly have set up the calculation, yeah, like to do a sort of epsilon type expansion, close to d equals 4. But I don't know if we've actually done it. Yeah, okay. I don't remember.
Okay. So then last question in the same direction. So in the case of KPZ, of course, exact solution has been quite useful, right? And is there a possibility that even for your model, there could be some integral version of your model in maybe 1D?
As I think I mentioned before to David, we didn't find this. I mean, okay, maybe someone else will figure it out, but we were unsuccessful in sort of distilling these equations into some more general form. or some simpler form. So.
Okay, thank you very much. Okay, we are more or less ending time, but are there any other questions or comments? Okay, if not, let's thank the speaker again.